So all right, I mean, so this area, so first of all, what's a hidden Markov model? So, supposedly stochastic processes was a prerequisite, I guess. I'll explain what it is, but it's basically trying to model this concept we talked about last lecture, where there's some state out there that we can't observe directly, but we have partial measurements, and that's true of every problem, And so, that's a generalization of a Markov chain. And then there is the control problem. So given this generalization of a Markov chain, we'd like to control these guys. And a partially observed MDP is just an HMM with control. All right, so I'll make that formal now. So we have our Markov chain X as before. No difference at all. All right, no difference. So let's, again, stick to, say, finite state spaces are countable. And finite, forget it. Finite state spaces, finite input space, all that. But there's also our observations, which are Y. Now, and so, so this is what we can actually see. This is we're reading, I don't know, Alex Jones's website. That's our observations. It doesn't mean it's true. It's just what we see, And from watching that observation process, we have some actions we can take. That's the little U there, and we control our environment, And so there could be tons of noise here, and tons of noise here, which means when we think we're doing something, something else happens. We say buy that stock, it doesn't get bought, something like that. Now, unfortunately, in order to do anything, you have to put in lots of assumptions. Okay, so again, this was a big assumption, assuming that the real world is Markovian is a big assumption, and then the only way to get anywhere here is to make the following assumption: is that you assume this model that the probability that y of t takes on some value y. Again, observation's discrete as well. I realize I don't care. I'm going to go back and forth between parentheses and subscripts. You should accept that by now. So there's a sort of Markov property for the observations, that if I look at the probability of observing a value y, given the entire past of inputs and xk's, and I can put in yk's as well if you like, that's just equal to something we'll denote q. Fxt. Right. So I gather all my information. I mean all of reality up to time t, and I like to look at how that influences my observation, and it only depends on the last state value, nothing else, and also there's no time dependence. So two big assumptions. Now putting a t there wouldn't be a big deal in terms of the theorem could present. That's like nothing, but the fact that this is sort of an IAD noise assumption is just that you can't do anything without some strong assumptions like that. All right. So a lot of literature is about trying to fit a model to data. You see, basically, there's no physics involved at all. You just take a bunch of data, you take y, a bunch of data y, and you construct a whole HMM from this. It's it's a way of doing data compression in a way. Or you have some oracle who gives you x and y, and then you try to go and come up with a model, the best estimate of a PU and a Q. Even though it's not really Markovian, you don't really have this memoryless property. you still just fit the best model of its form. Okay? Okay, and I would say that a lot of this, maybe this part of this, so I'll give you handouts, so once these are corrected a few more times. I think a lot of this is more philosophical, you know. Basically, you know, you get an idea, that's the structure of the optimal control problem, and then it gives you all sorts of insight about how to come up with architectures for approximate control, you know. I think that rarely do people actually follow this cookbook as a way to control a problem, but they get inspiration from it. All right, so that's just a warning. Okay, so there's lots and lots of viewpoints. So anyway, yeah, first, also nothing else changes. Our objective, say average cost, exactly as before. You know, one goal might be to try to minimize this over all input sequences, but the big difference is this is the observations. So you are, but UK is some function, say phi k, of y0 ... yk. All right. So we can only look at those observations. We don't have access to the state directly. So the first person to look at this and think they could actually get anywhere with it must have been scared to death. You know, it looks like there's no structure at all. No?
Divide by n, right?
Oh yeah. Thank you. Yeah. All right. All right. So now in real life, you'll have a realization of this. You know, I've told you before that Markov chains look like this. And what have I called in the past? I guess nk plus 1. You know, every Markov chain has this realization. And this memoryless property here just says that yk plus 1 is another function of xk plus 1 and then another disturbance. All right. Cool. That's it. So these guys are ID. And also N and W are mutually independent. Yeah, if there's some sort of a correlation between these noises, everything will get more complicated, and you know, yeah. So this is, yeah, but you can do it, but forget it. Yeah.
So here,
yeah.
Honestly, we do look at like past observations as well. Is there a very specific reason we do that?
Well, Jesus, I mean, can you imagine if YK, suppose XK took on, XK was like the financial application I talked about. It was just, you know, Trump's tweets, Alex Jones' rants, you know, diseases in Iran, all of this stuff. And then YK took on value 0, 1. You know, I mean, you only had 1 bit, you know, maybe per minute, but you know, you only had 1 bit. I mean, you know, you've got to. There's no way that an optimal solution will only depend on the last observation, and that'll be almost never. And so this is the problem. Is it looks like as time goes on, you've got your function gets more and more complex. Everything explodes, and that's what I mean about bravery. To look at this problem and think you can get anywhere at all, you'd have to be pretty, you know, pretty brave, you know. Yeah, and but it's amazing how this falls apart. It's remarkable, So, yeah, so let's see. So this is, let's say, one, you know, terminology. So first of all, this would be called I mean, this here, I should say, that together, I guess, is a controlled HMM, right? You know, and it's, if there was no control, if U was just not there, then it would just be an HMM, just to be sure. And 3, this Palm MDP business. It's awful, isn't it? The terminology. So a partially observed MDP is simply a controlled hidden Markov model with some objective, with some optimization objective. Yeah, and there's some really, there's a really funny terminology that comes up here. I'll give you some of it, and maybe we'll make up some of our own as well. I don't know. And a warning: don't go to Wikipedia. I did yesterday to try to maybe, I don't know, to see. Well, partly because my notes were really messed up, and I thought maybe I could get some ideas to fix them up. And Wikipedia, it seems to be gobbledygook to me. I don't think that. I don't know, it's just ramblings. And so I want to try to correct Wikipedia today, go through and write down what they should have written down in that article. All right. Here's the magic. Yeah. Actually, I should hold off on the magic, shouldn't I? No. That's terrible. That's terrible. I'm not going to show you the magic. Let's just look at this. Let's scare ourselves a bit more before we. I don't know. I'm jumping 3 pages ahead. Where's the eraser? Did Neil take it with him? Oh, right there.
No, it's not.
That's not it. Yeah. Okay. Thank you. No. Okay. So get rid of this terminology. Screw that. All right, so what am I going to do? I'm going to look at the finer horizon control problem. So let's make things simpler. Rather than jumping to this really complicated average cost setting, let's look at the simplest case. Let's look at, I'm going to look at the minimum over all these U's. And I want to solve this problem today. All right? So I've got a one-step cost like over there. I've got a terminal cost as well. And I've got my U0 to UN minus 1. But remember, I'm restricting to inputs of this form. You know, I could make this randomized as well, but then I'd have more notation to deal with. And in the end, we find out we don't need randomization. So, you know, we've just got a deterministic function of the observations. So this looks incredibly hard. But if you go back and if you just go back and review the notes on dynamic programming and this notion of a cost to go, that would be your starting point in trying to understand this thing, you know? All right? And so just imagine this. Like, how would you formulate a cost to go? So I don't know if this is how the first people who did this thought about it, but it's really instructive to think about this. So basically, I'm writing the system up to some intermediate time, n, and say some arbitrary input up to time n, and then I want to look at the what am I going to do for the future? Okay, so the definition would be this. So I'm at time n, and my horizon is capital N, because that's the last state we look at. And I'm going to define that to be a minimum of exactly this expectation, but again, it's cost to go from time n. So it's from n to n minus 1. But then it's a function of our observations. So I'm going to put a conditional expectation there, yn. All right. So so yn is a sigma algebra. Okay. And we all know that when I compute a conditional expectation like that, it's a function of the observations. So this cost to go function is some crazy function of the observations. You could write this as, say, G star well, I write it like this. It's like y0 dot dot yn. Now, the u's are a function of the y, so it's redundant to put those in, but it's useful to put them in. Right? I mean, u is a function of y, so adding that, it's redundant. It doesn't make any sense. But it's just useful to think about this way, because what I'm doing here is I'm putting an arbitrary input up until time n minus 1, right? And then I'm looking at and then I'm optimizing just from n onwards. And this gives me, wherever I ended up with, this gives me the remaining cost to go. Is that clear? And it's now a function of everything. It gets more and more complex as little n gets larger. I'm minimizing from n to n minus 1, so there should be a minus 1 there. Yeah. Because we're taking u little n to n minus 1, those as variables we optimize. Does that make sense? I mean, this is consistent with our intuition about me wandering around. I end up here. I had an optimal path up to here. What do I do next? Well, I would solve this problem. I would go through and do this optimization based on what I've seen up till now and optimize the future, right? All right. So this is hopeless, right? Because again, we have this complexity. We have the cost to go grows in complexity. So what you need is a sufficient statistic. Oh, really? Yeah. No, it's a beautiful word. So the term sufficient statistic comes up when you see this explosion in data. As time goes on, the data gets bigger and bigger and bigger. What that means is you want a sequence of, we want a sequence, I'll call it I0 dot dot dot. So we want a sequence here that, that captures the information. Now, so instead of G star being a function of all this, it's just a function of the i's, all right? And you could always take in just to be this whole string. So the trick is that you want the state space in which in evolves to be fixed. So you don't have this explosion in dimension as time goes on. So ik is in some set, I don't know, I for all k. Well, this might be a little bit complex, but it's fixed. It doesn't go with time. And then we want this monster to be equal to, I'll keep the notation I have here. Oh, wait a second. Oh, shit. Oh, shit. Oh, well. It appears I was very careful with my notes, but I really should have done that. Okay, I'm still correcting these notes. You know, that was a perfectly valid definition, but I want to keep UN as a variable. So I will get rid of, I'll make that UN there and just optimize onwards, okay? So I've already chosen my UN, and I'm optimizing the future use. Okay, so I want, instead of Vn to be a function of all this, I want this to be some, I use script V star. And I think I put a star here as well. Let's put stars to emphasize optimality. That's just a function of the information, I mean this information state or whatever, and the input. All right, so I just use a new term. We don't, any more pens? So you'll see this, so it's a sufficient statistic, we can come with 100,000 terms. It's also called an information state. And you can imagine the different communities. So sufficient statistic is a term you see in statistics. Information state is a term you might see in a control audience. You know, but it's exactly the same thing. All right. So that's the goal, right? If we could come up with a sufficient statistic, that would be really awesome. Imagine if you could find a sufficient statistic that actually was a controlled Markov chain. The whole thing would boil down to just a fully observed MDP. And that's what happens. Yeah. So it exists, and it's Markovian. And so I've got a whole list of beautiful facts. So what I want to, you know, in spite of the allergies that are driving me crazy at the moment, I'm going to show you that yes, IN exists. I can take Bn equals IN is the conditional distribution of x given y. Okay, so specifically what I mean by that is Bn is a function on the state space. Bn of x equals the probability that xn equals x given y0 to yn. Right? And, you know, what's the only thing hard in this material is the damn notation. Because you notice that I've written Bn of x. It's a function of x. But of course it's a random variable. And sometimes also you think of it as a function of the data. So you could also write Bn of x semicolon y0 dot 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 yn given the observations. I'm doing this for two reasons. I mean, one, to remind you, conditional probabilities, conditional expectations are just functions of the data. So whenever you write a conditional expectation, it's a function of the data, all right? But we suppress that because that's been observed, and we just say that's a random vector, you think about it. Because x takes on a finite number of values, and so it's just think of it as a random vector, all right? So that's fact, big fact number one is that we can do that, and I'll show you why. You know, it's a yeah, I'll explain. I mean, I will show you this in about, in 15 minutes. All right. So what's the state space for Bn? Okay, so again, I said it's a finite state space. Say the states are x1 through xd. D could be 10 million. It's it could be a big state space, but it's finite. And so this sufficient statistic here evolves on this unfortunately no longer finite state space. So we start out with a finite action space, a finite state space. Everything was finite, and suddenly now we're evolving on this continuous region. That's sad, okay, but that's what you get. All right. So it's a subset of RD. It's a d minus one dimensional subspace. Region. And so it is a controlled Markov model. Which is absolutely crazy, all right? So, we will come up with a description of this. So, we're saying is that the probability that Bn is in some set S, for S a subset of this simplex, the probability for any measurable set S in the simplex, probably this belief state, it's called the belief state. More terminology. More terminology. You'll see that everywhere. Don't worry about it, okay? It's a conditional distribution of xn given yn, but it's called the belief state in the literature. And can you tell the joke for me? Well, let me have a go. Let me do it really, let me do it. So what was this called in the 60s? It was called the information state. And the 80s, the belief state. What should it be called this year? Deep state, all right. All right, so it's a deep state. Oh, it did work. Okay, so the probability that at time n, the deep state is in a set S at time n, given Bn minus 1 equals B, and U n minus 1, that's right, the previous U, equals little u. We will come up with some crazy function for that. It will be, we need new notation or something, but some, I don't know, Z or something, Zorro, sub U from B to S, in quotes. I really mean, and everything else, and y0 ... yn. All right, so if I want to know the probability of my belief state, like conditional distribution, is in a set S given all the past information, and that should be -1. Yeah. So all the past information, n-1, n-1, n-1. The previous observations are irrelevant. Everything else is irrelevant. If you want to, I'll put in the b0 ... bn-2. These are all functions of the y, so that's redundant, okay? But just so everything you know in here, the only thing that matters is the last u that you put in and the last belief state that you observed. And you observed it because you computed it. You know, we're going to compute these guys. It's a nonlinear filter you can run. Yeah.
So I guess here the policy for un-1 will be just dependent only on the belief state.
Well, there it is. I mean, well, no, you don't know that yet, right? Because, so, we're almost there. So you're jumping ahead a bit. I mean, here we're saying something that's suggestive. We're saying that this cost to go function is just a function of Bn and Un. But we haven't quite been able to embed the original problem into the new controlled Markov chain, and that's next. Okay, and that's exactly next. So we've got a state space, we've got control dynamics, which I'll write down for you, I hope. And then we have to translate the original problem into this problem. Okay, so we've got this horrendous problem here that we'd like to solve. We have these strong restrictions on the u's. And then we want to translate it. Well, you know, this is, you know, n is deterministic here. You know, we can just look at each term separately. Like, take one of the expectations. You know, that doesn't fit because I've got a controlled Markov chain, but I want a cost function on Bn and Un, not on Xn and Un. All right? So which property am I going to use? Conditional expectations. What? Smoothing, yeah. Right. Okay. Now, UK is already YK measurable. So you can just think of UK as fixed, and you're just taking the mean of a function of xk. All right. But how do you take, once you have a conditional probability, you can take a conditional expectation of any function of x. So this is equal to the expectation of, inside here, the summation over all x of bk of x okay, so bk of x is a probability that xk equals x given the observations up to time k times c of xu. There it is. So I can take my cost as a function of x and u and replace it by a function of b and u, all right? And notice that it's linear. You know, it's linear in b, which is pretty fucking awesome, to use my language. So I can just define some script c of bu to be equal to this dot product. Right. Because the expectation of the thing I'm interested here is precisely the same as this. I get rid of x, and I replace it with something I observe. And the same thing is true at the end, right? You know, I can define some, unfortunately I would use the script v, but big deal, script v0 is just going to be equal to, you know, to the conditional expectation here. So yes, now you're right. See, we've got our value function here is exactly equal to the minimum over u0 to n minus 1. The same expectation, but here I can replace it by this crazy script thing. And then the terminal guy again I can replace by this this linear function of b at the end, right? Because the same thing. The expectation of this, right? Smoothing property again. The expectation of this is the expectation of that. And so I get the expectation of this, that's my friend here. Yeah. Okay. I think it's ingenious. And so the cost to go can be expressed in that way too. Of course. I mean, we already said that.
So the main thing we did is just encode everything into a belief state?
Well, yeah, so I mean, but so far the only thing we've done is I've made a bold claim of the existence of a deep state.